off to the races. I'll need this mic here to. Hello, thank you everybody for coming to the last talk before lunch. I'm very pleased to introduce Hillel Wayne. He is a formal methods warrior, a chocolatier, a code nurse. He goes by many names, and today he's going to be talking to us about beyond unit tests, taking your testing to the next level. Let's give him a round of applause.
First of all, can everybody hear me? Okay, great. So my name's Hillel. Thank you so much for coming to my talk, Beyond Unit Tests. We're going to be covering today generative testing, design by contract, full and partial specification, and formal methods. And if none of those words made any sense to you, you've come to the right talk. Before we begin, I just want to get some quick logistics out of the way. Shout out to the PyCon volunteers. Alex walked me here, Jay, who's the current session host, and Stanley, who's doing the audio captioning. I'm a Vim user, so I am incredibly jealous of stenography. They're amazing. So also what happens is I figured a talk just before lunch, I should probably make sure that nobody's hangry. So I decided to bring granola bars for everybody that I made. I believe Jay has them. I was not expecting there to be, though, like 20 million people. So there's only about 100 granola bars. So I mean, you can come up during the talk, just grab one from Jay. And the ingredients are just behind, are right over there. So if you're allergic to any of these things, please stay away. There will not be questions after this talk. There will not be recorded questions. I'm going to be around, of course, the rest of the conference. And I have a Twitter and email and such. You can email me anything you want. Just hunt me down, ask me anything. And what happens is that I'm going to be putting all of the questions I get and the answers at this site. So if you don't have a chance to ask anything, you'll still be able to see everything everybody else asked. And then finally, I do have to mention this right now. This code will not be Pythonic because I want to fit it on a slide. Do not follow my standards. They are bad standards. So first of all, does everybody here know what unit tests are? Show of hands. Okay, great, most of you. For those of you who don't, and I guess the YouTube crowd, unit tests are small functions we write that, well, test our code. For example, if I was writing add, I might write, say, 1 plus 2 is 3. And we're using PyTest here for the record. I prefer it to unit test 2. We might also write, okay, maybe 0 plus 0 is 0. Adding something to 0 still gives you that number. And let's add a negative in there. Now we've got our unit tests for add. And the thing is that this talk is admittedly called Beyond Unit Tests. But fundamentally, unit tests do make up the basis of what we consider good code behavior. So I'm going to have to put this in the very beginning. Write your unit tests. Write your unit tests. Write unit tests. Okay, so now let's go beyond unit tests. Normally when people think of going beyond unit tests, they think about integration tests, things that test larger parts of your code. And then beyond that is acceptance testing. This creates a sort of pyramid where the easiest and small stuff's on the bottom, and your harder and more comprehensive stuff is on the top. We're going to burn all of that down right now. See, the thing is that all this counts as what we call auto manual testing or example testing, because you are by hand writing every single test that the computer is automatically running. And again, this is still very good, but it does also have some major limitations. Let's go back to that add example. Here's my state space. On the x-axis is x, on the y-axis is y. What this says is that this is all the possible points that we could input into add. So 1, 2 is basically that point. Or we could test the origin, that's that. Our third test was, I believe, 1, 0, that's over here. And our fourth test is there, right? Great, we've covered a lot of our state space. But have we really? We've missed 2 whole quadrants of all the inputs we can get into add. That's a lot of space. And furthermore, what if there's some edge cases there? We've completely missed them if there are. Now you might think, well, as a simple function, of course there's not going to be any mistakes we made here. But what about more complicated functions? What about clamp? That's going to have a 3D state space. Now you have 3 integers instead of 2. Or what about, say, the slope between 2 points? That's going to be some sort of weird, janky hypercube of a space. Or what if you don't even know what the state space of your function is? What about left pad? What even is the state space of left pad? Are you sure right now you could think of every single edge case that left pad has to deal with on the spot? Probably not. So we need something that's better than auto manual testing, so we don't have to hand roll every possible edge case we can think of. We need some way of generalizing this. This is what we call property-based testing. This is not Python properties, for the record. This came from a different community. We're talking about the properties of our code. Another term would be invariant testing. Now, I could go into the theory of what this looks like, but I think practice is just a lot easier to see. So let's actually walk through an example. I'm going to use the hypothesis library, which is arguably one of the best testing libraries of any programming language out there. Not just dynamic languages, not just scripting languages, just any language, period. This is by David McIver, who is a genius and has actually keynoted a few of these conferences. Great dude. So here's my generative test. I'm going to say, if you add any number to 0, you get the same number back. It looks exactly like any other kind of test. Let's actually zoom in on that. So this is like any other kind of test you'd write, saying adding to 0 gives you the same number back. That's our invariant, that's our property, that 0 is the identity of addition. The only difference between this and any other test you'd write is that given decorator right over there. And what that does is it tells PyTest that, hey, this is no longer a single test. This is now an entire template of tests. Take anything that matches the strategy, in this case, the integers is the strategy, and create all the tests you can think of from that. And PyTest will oblige. Let's see what this looks like when we run it. Well, that looked like any other kind of thing you'd write. You see that even though we ran about 100 tests, 1 dot. So let's actually show what it's actually doing. And to do that, I added some logging and made PyTest show us all the logging. Here's what happens when we do that. So it might be a bit hard to see right now, but we've tested, first of all, every number between 1 and 20, 0 and 20. Then we've also tested massive numbers, huge negative numbers, and every pathological input we can find. In fact, if you put in something else, like if your strategy is strings, it will try Chinese characters, it'll try Unicode characters, it'll try 10,000 non-breaking spaces. It is looking for the edge cases that we as humans tend to miss. Okay, so that's what it looks like when it succeeds. Now let's make it fail. To do that, I'm going to try another property. This property is going to be that addition is commutative. What that means is that a plus b is always the same as b plus a. Now I need 2 inputs, 2 strategies. We can trivially extend our decorator, our given, to cover that by just adding another parameter. So let's see what happens when we run this. We've gotten an error. It turns out our function was not, in fact, commutative. I'm actually going to zoom in on the next slide, just like that. So here's what actually is happening here. It looks pretty much like any other failure, except it also gives us the inputs it tried. It said, if a is 0 and b is 1, then for some reason, our add function gives us 0 on one side and 1 on the other. That doesn't make any sense. Well, that's because here was my add function. Look, it passed the unit test. That meant it was correct, okay? So generally when I bring up this topic, people tend to have 2 questions about it. The first is that if we're looking at randomized testing, how do we catch regressions? And it turns out that hypothesis, again, very sophisticated, will cache every single failure it finds and try them in all future runs. So now if I fix my add function, what's going to happen is it's going to try 1, 0 no matter what. Additionally, we can add a specific example over here, which makes it try that every single time. But even so, remember, we're still going beyond unit tests. We're not replacing them. And the general strategy is to make our unit tests pin down the correct behavior, and the property tests sweep our entire state space for the wrong behavior. Well, then the other problem is that you might see that, how do we find good properties? So I'd like to go through a more worked example. And it turns out that when you use property-based testing, you tend to think of patterns of testing much the same way you think of patterns of code. So let's do a more complicated example. This is the max product of the pair of a list. For a given list, return the maximum possible product of 2 elements in it. So for here, 5 times 2 is 10. 1 times 5 is 5, 1 times 0 is 0. So the result should be 10. Following? Great. So I asked a very smart friend of mine who's actually presenting at Scala in Berlin to write a function that does this. Here's what he came up with. First, we check that it has enough elements, because he is very careful, very defensive programmer. And if it not, we raise the best Python error. Then what we do is we sort the list and take the top 2 elements, and then we multiply them together. I also asked him to write some unit tests. He wrote these. And this is, again, a very good coverage. We're trying pathological inputs. We're trying large inputs. We're trying sort of disconnected inputs, all sorts of stuff. So quick show of hands. Who here, on seeing that code and seeing these tests, would be reasonably confident it was correct? Okay, so about half of you. That's good. I figure some of you might be seeing where the bug is right now, and some of you might not, which is how this works. We're human. We don't see everything. So let's first get something that works. I can write a property test that gives now a list of integers. It'll try not just like an empty list. It'll try like 1 element, 2 elements, 20 elements. It allows us to nest our strategies. If we run this, though, it'll try the empty list and immediately fail. But that's not a valid input anyway, so we need to make sure that it only tries elements of size 2 or more. We can do that by just adding a parameter to our strategy. Min size is going to be equal to 2. And now this particular property test will pass. So let's look for a more complicated property. Let's say I have this as an input. The maximum product is going to be 5 times 8, right? That's 40. By being the maximum product, that means it's the highest possible. So if I pick any other pair of numbers, such as the first 2 numbers, I should get a value less or equal to the maximum. We can encode that like this. We assert the max product is always greater than or equal to the first 2. And this might seem a bit of a creative leap, but again, once you start working with these kinds of technologies, you start to see these properties pretty quickly. And if we run this, we're going to find an error. It turns out that we did not at all factor in for negative numbers. And remember, multiplying 2 negative numbers gives you a positive number. So -1 times -1 is 1, but the maximum 2 that we sorted are 0 and -1, which gives us 0. 0 is less than 1. Okay, so property tests do give us some pretty good power for covering unit tests. But I tend to be pretty ambitious with these things. I want to go further. I want to see if we can use this to extend it to integration testing. Now, the problem with integration testing is that it's just way more complicated to do, because instead of having just a single nicely type-written function, you have all these modules talking to all these other modules. First of all, that makes finding a good property to test very tricky. But worse, what happens if we get an error? What happens if we find our property was broken? Well, we're going to get that there's some bug somewhere. Is it in A? Is it in B? Where is it? We don't know. So ideally, what we want is some way of using property tests to give us good invariants that we can easily discover for a large system, and also localize the problem. These are actually really hard things to do, which is why most testers, especially Agilists, go, okay, just write as few integration tests as you can and write as many unit tests as you can. But again, we don't like that. We're humanity. We shot a car into space. We should be able to write some integration tests. And it turns out there's actually a really elegant way to do this. But in order to sort of see that, we're going to have to take a detour into MyPI. Just a detour, I promise. Who here has heard of MyPI? Again, most of you. This is great. So MyPI is a separate program that looks for static type errors in Python code. It is developed by the core Python foundation, so it is an official tool, but it exists independently from Python. What happens is that you can add type annotations to your code. Say, add takes in an integer and returns an integer. Now, what's going to happen is that if I do something that's wrong, say string of x plus y, and then I run MyPI, it'll give me this specific error. Incompatible return value type, got string, expected int. Now, here's the really fascinating thing about this to me. It didn't say there's a bug. It didn't even say there's a bug with this function. It said there's a bug here in the output. That meant it was able to, just by the inputs, localize the bug to the function itself. Not something calling it, not something it called to, but what the function did. Furthermore, if I say have a correct function and call with g, add a 1 and a string 2, it'll also localize the bug to this specific parameter. It knows that the function may or may not be correct, but our input is definitely broken. Now, this is actually pretty cool stuff, because when we're talking about that integration chain of things, we had no way of localizing. This does localize. So people tend to get a bit euphoric about static typing, and they're just like, types will save us. Hooray, we've got our answer. But again, no, that does not work at all. This is not actually going to be the answer. And the reason why is because not just in Python, but in almost every language out there outside of some niche academic research languages, you can't do all that much with types. You can specify some structure, but you can't do any behavior. It exists as an independent system from your code. What we really want is a way to use the full power of the language to test our code and verify it's correct. And we can't do that with static types. But we can do that at runtime. Here's how we could rewrite this to do our type checking at runtime instead of at compile time. Exact same thing, except we now have our requirements that we assert that the instance that x and y are going to be integers, and we ensure that our output is going to be z. These are assert statements. If any of them are wrong, we raise an assertion error. So now at runtime, we are doing the exact same thing as we did at compile time with MyPI. Which, this may not actually be that exciting, but the thing is that now we've opened up our entire space of Python to write any kind of assertions, any kind of checks we want. So let's see how this applies to a more complex example. Let's try tail. For a given list, return all but the first element of it. So tail of 921a should be just 21a, right? Turns out that, again, in most languages, there's no way to cover this in just the type system, because there's no way to sort of distinguish between getting the tail and getting everything but the last element. Try it. So let's try to do this now at runtime. First of all, let's start with our type check version. We take in any kind of list, and we output any kind of list, and we return the empty list. This type checks, again, type checks correct, we're done. But of course, if I pass in 1, 2, 3, I'm going to get back the empty list. That's not at all what we want. That has nothing to do with what we actually intended. So we want to sort of, in some way, validate that our output is correct. And to do that, we need to ask ourselves, what does tail actually look like? If I take the tail of an element and add that to the element we cut off, we get back our original list. Is that correct? Right. In fact, essentially, head plus tail equals L. So let's actually make that an assertion. We use a temporary variable output, and we assert that the first element appended to the beginning of the output is equal to L. Now what happens is that if we run this, we get a type error, an assertion error. I added this post condition as logging. It wasn't part of there. Again, not Pythonic. So now what's interesting about this is that if I now write a correct version, L1 colon, just take the slice, and I run this, now it works just fine, no error. So this gets us our post condition, this is called. But we also want to make sure that we can't call our function with bad things, just as we shouldn't be able to call it with a string. So in this case, what is one possible bad thing we can call it with? That is the empty list, which is going to give us an index error. Tail is not defined for the empty list. It doesn't make sense to get the tail of an empty list. So we don't just want to raise an index error. We want to fundamentally ban it. Say stop the program from running if we encounter this, because something somewhere else in the chain did something wrong to cause this. So we can add what's called a precondition and assert that the length of L is greater than 0. Note that you could also write assert L here, because empty lists are falsy, but I really wanted to emphasize that we want the length to be more than 0. Now if we call with an empty list, we get a precondition error. So this now gives us what we call contracts. Designed by contract is this idea of embedding assertions that must be true in the code. And if an assertion is false, we crash, start over, and look for the bug. And this may seem very simple, but it turns out this is actually one of the most powerful verification techniques we know about. We've seen it work empirically at scale in all sorts of places, but these places have mostly been avionics, critical systems, defense, academia, so nobody's heard of this thing, which honestly I find completely crazy. I mean, here's a question. How many of you have heard of Ada? How many of you actually looked into what Ada can do? Okay, I've actually done some experimentation. You can do incredible things with Ada, but because it's Ada, nobody cares. Let's port it to Python. First, we need a library, because we like our libraries. But the problem is that, as mentioned, these are very, very obscure, unfortunately obscure techniques that don't deserve to be this obscure, which means poor libraries. There's a few different contracts libraries for Python. The one I'm going to use is called Contracts by Rob King. This is because almost all of the other libraries are just about type checking at runtime. We don't need that. We already have MyPI. That really discounts the power we can get from contracts. So let's now rewrite this using this library. So we have, first of all, a require decorator, where we give in the property, and we give in a function that's Boolean. And the function, if it returns true, great. If it returns false, assertion error. This actually has access to all of the arguments we pass in. So we can say args.l instead of L. Now we don't need that. We've gotten our precondition. Similarly, we can have a post condition, our ensure. And this is the exact same as our precondition, except we also have access to the output. So we can get rid of that. And in fact, since this has the output, we don't even need our temporary variable anymore. We can just return 1L. Okay, great, we're done. But what was the point of all this? Like, great, we now just added a bunch of stuff to our tail function. What does that actually give us? Here's where things start to get really cool in my opinion. What property test could we write for tail now? Well, first of all, I'll give you one hint. We need to make sure that in order to satisfy the precondition, we pass in lists of at least length 1. Now, I want to give you all a few seconds to think of what you think would be a good property test here. Everybody got an idea? Here's what I'd write. That's it. It turns out that with our contracts, we have done a full specification of tail. We have precisely and totally and formally defined what it means to be a tail function. And this means that any deviation from that idea is going to trigger a contract error. And that means all we need to do to test tail is correct is to just call it with different inputs and make sure that all the contracts are satisfied. And the thing is that this may seem like a toy example, but we can actually do this for a lot of different functions. In fact, let's actually go to our max prod thing. It turns out that contracts are usually designed for testing and development, not runtime. So they're allowed to be very slow. And I can write this. Is this the maximum product? How do we do that? We just brute force every possible combination of indices, multiply them together, make sure it's less than the max. That'll work for our isMaxProd thing, but it's also going to be incredibly, incredibly slow. But we don't care, we're just doing testing. So if we write an efficient version, we can simply make isMaxProd our ensure. And then all we need to do to sort of completely, again, fully test this function is just call it. Just call it in a property test. And now we have all the tests we need to make sure that maxProd is correct. Now, admittedly, you can't always get full specification. You can get it for pure functions, but once you start adding in things like mutation or globality or third-party systems, it gets tougher. But honestly, the main value isn't just in full specification. Even partial specification, where we add some properties, is still enough to give us something really incredible, in my opinion. Contracts plus property tests are integration tests. What do I mean by this? Let's go back to our entire chain of calls. This is no longer an accurate representation of what we're actually doing, because we really have something more like this. A calls B and exercises B's requirements. When B returns to A, it has its own post conditions. Then B calls C and F, and it has their requirements, and so on and so forth. So first of all, what this gives us is a large number of invariants to check. Every contract must be satisfied. That's a good invariant, isn't it? But more importantly, what happens is that any error is now localized to where it's caused to. So for example, if F is called by B and violates F's precondition, we get an error right then. And not only that, but we now know it's probably in B. We've localized where we have to look for the bug in our integrated system to the B module. Similarly, if B is fine, but F fails, we're going to get a post-condition error on F. And we immediately now know, just by looking at the error we got back, that F is where the bug is. Even though we've put in the property test on A, it's able to say, okay, you called A with your property test, F's the bug. And if B returns something wrong to A, we know it probably called C and F correctly, but the way it combined the data of C and F is where the bug is. Again, not totally certain, but very likely. And it's very, very unlikely that it's in D or E or even necessarily F. We've cut out half of the modules which could possibly contain the bug just by using contracts. So this has actually been shown in a lot of different code bases at scale. This is how we tend to do high correctness, high assurance software. And not only that, but we can go further. We can extend both of these ideas to even further to cover more stuff. I'm going to cover this a bit less because I didn't want to make this the thrust of the topic, but just as a quick overview. First of all, we have class invariants. And these are properties that must hold true on classes with internal state. Every time bank account has a public method called, it can go through all its private methods at once. But by the time it's done, no overdrafts must be true. So now we can say, if there's any sort of state mutation, we can validate that the mutation we make in our state does not leave the system in an incompatible state. This gives us stateful testing, gives us mutable state testing. Similarly, we have this concept called stateful testing or model-driven testing from Hypothesis. And what this is we tell Hypothesis not just what inputs it can try, but what functions it's allowed to call. Here it can say, for example, I'm going to call addNum twice with 3 and 5, and then call the reciprocal function, and then call the reciprocal function again, and then call addNum 5 more times. It's allowed to choose both the inputs, the ordering, and the number of steps. This allows us to, when pointed at a full system, basically get full-on acceptance testing. We can simulate users clicking around randomly on our site. We can simulate third-party systems causing crashes. We can simulate whatever we want with this, and we can use it to snake through all of our code, once again looking for the most subtle, most critical bugs. And then we can get into even crazier stuff. This is not quite in Python, but all of this is portable to Python in different libraries. We have, first of all, testing generators in Clojure. Clojure can look at the contracts on code and figure out what inputs are allowed for our property tests. It can say, oh yes, here are your contracts, so our property test must be generated with just even integers. In Eiffel, we can actually compose contracts in classes. We can have inheritance rules based on how the contracts inherit between classes. And it's able to use this to actually formalize a really elegant view of OOP that you don't see anywhere else in any other language, that basically allows you to say OOP is the language of formal verification. In Ada, we can actually assert global effects in our contracts. We can say a line of code is not allowed to, in any of its changes, any of its chain of functions or procedure calls, affect a certain kind of global state, or must affect some other kind of global state, or must log or not log. And this, once again, extends the kind of power we can do with this kind of specification. In Daphne, we have this thing called static verification, where we can just, by looking at the contracts, the compiler can go, nope, there's a bug here. Don't even need to run it, don't even need to find any tests. Looking at these contracts, looking at the body of the code, there's a bug. And then finally, I think that there's some really amazing stuff we can do in Python too. For example, with abstract-based classes and subclass hook, we can do some really fascinating things with runtime dynamic metatyping, which hasn't really been explored really in any language out there, but I've been working on a couple of toy examples, and I'm hoping on doing more with this. So that really covers the core of what I want to talk about. The quick wrap-up is that we have unit tests that generalize to property tests. We have MyPI can generalize to this thing called contracts. And we have integration tests, which essentially generalize to a combination of property tests and contracts. Now, here were the two things I used, hypothesis and contracts. I'm going to leave these on here for a little bit just so people can write them down if they want. 1, 2, 3, 4, 5. And now I'd like to just conclude with a couple of thoughts. First is the core of this talk. None of this is going to help you if you don't have a solid base, and unit tests make your solid base. Second, I haven't really talked about what this idea is called, and this is what we call formal methods. This is the study of how we can prove software is correct at a level not seen in any kind of modern-day production language. Nothing really approaches the level that we can do with formal methods. Actually, yeah, Ada can do it, never mind. But this has mostly been a very niche technique in certain industries and in academia, and nobody's really thought about how we can apply it to all languages out there. And it turns out that this thing that I was talking about, combining property testing and contracts, is one of the ideas that comes from this that we can easily use in any other language we want, especially Python. So there's some really amazing ideas here that just haven't been explored anywhere. And I really think that a lot of the next value in the next 10 years, most of our big boosts in correctness are going to come from us finally learning how to use formal methods in the real world. If this is something that might interest you, Jay and I are actually hosting a formal methods open space tomorrow, Saturday, 2 p.m. We'll probably be talking about formal specifications, so TLA plus and alloy, and then maybe if anybody's interested, theorem proving, or if anybody wants to see what Daphne or Ada Spark code looks like, we can probably whip that up too. And that pretty much concludes what I wanted to say. Again, my name is Hillel. You can find me on Twitter at Hillelogram and my site at Hillel Wayne. Thank you so much for coming, and I look forward to the rest of the conference.